Okay, now that we know how the Michaelis-Menten equation was derived, we're going to talk about how to use it and try to conceptualize it in our head. So here it is, right? V naught equals V max times substrate concentration over Km plus substrate concentration. Now, what does V naught mean? Well, V is velocity and 0 is V0 or V naught is the initial velocity. We talked about that a little bit in lab. You want to test the initial velocity for reactions, and that's when the substrate is in abundance, right? You put a little bit of enzyme in your reaction, a lot of substrate, and under those circumstances, the assumptions that we made in our Michaelis-Menten derivation are most true. The enzyme is most busy because it doesn't have to hunt for substrate, and the concentration of the total enzyme approaches the concentration of the enzyme substrate complex. So that's what the V naught means, initial velocity under saturating substrate conditions. Vmax, we talked about what that means, the maximal velocity. Substrate concentration, that makes sense. And Km still doesn't make sense. So we're going to have to figure out what the heck Km is. Right now, with our derivation, we just know that the Km is some jumble of rate constants that don't make a whole lot of sense. So how are we going to figure out what this equation can do for us and how can we conceptualize something like Km? Well, before we do that, really it's important to mention that this Michaelis-Menten equation is really famous and very useful for any biochemist who's doing kinetics, because really what it allows you to do is if you know the Vmax in Km for a particular enzyme, catalyzed reaction, you can calculate the rate of that reaction at any substrate concentration, and that's very useful if you're trying to manipulate those reactions. So how are we going to look at this equation as something a little meatier instead of just something we're going to plug values into? Well, the first thing we're going to do is try to plot it. So we're going to plot V naught versus substrate concentration and see how the rate of this reaction changes as you change substrate. So here's the plot. So on the y-axis, let me change the color of the pen here. The y-axis is our V naught, right? Our initial velocity. And the x-axis is substrate concentration. So when we plot the Michaelis-Menten equation, we see a curve form. And a lot of this curve makes sense, right? If we have no substrate, then we have no velocity, right? We're not making any product. As we add some substrate, the rate or velocity of this reaction increases rapidly, goes up, and we sort of get diminishing returns as we keep adding substrate. We talked about this in lab a little bit also, is if you have a lot of substrate in your reaction, your enzyme's really doing as much work as it can do. It doesn't have to find the substrate. It's at high enough concentration that that enzyme substrate complex is forming really rapidly. And out here, it makes a lot of sense. If you envision that enzyme in the reaction tube just, with tons of substrate all around it, it doesn't really speed things up a whole lot if you dump in another shovelful of substrate. The enzyme's sitting there working as hard as it can. And you can see that this curve is really approaching the Vmax, the maximal velocity for the reaction. Right? It doesn't go up as a line. Now, so Vmax we can conceptualize, right? As we add more and more substrate, the reaction is going to approach its maximal velocity. But also, using this plot, we can start to conceptualize what this Km means. And the first thing to notice is that Km is a substrate concentration. We've got Km down here on the x-axis as a substrate concentration. And the best way to think about Km is as a substrate concentration. Now, if we go back to our equation here, we can do a little bit of work to try to figure out exactly what substrate concentration Km is. Now, if Km, which we know to be a substrate concentration, is equal to the substrate concentration, if these two things are equal, then the denominator of our equation here is going to equal the 2 times the concentration of substrate. Concentration of substrate plus concentration of substrate is 2 times the concentration of substrate. And if we, cancel out this substrate concentration with the one below, we'll find that the velocity of that reaction is equal to 1/2 Vmax. And so what that little bit of math tells us is that Km is the substrate concentration where my reaction reaches half of its maximal velocity. So if we know the Vmax for a reaction, then we know what half of that rate is. And we can look at a curve like this and say Km is equal to the substrate concentration where we've reached half of our maximal velocity. That's a really useful way to think about Km. It is the substrate concentration where we've reached half of our maximal velocity. And really, Km is a good measure of the affinity between the enzyme and the substrate. If it takes a whole lot of substrate to reach the maximal velocity, that means your enzyme doesn't really like to bind to it very much. And you've got to increase the concentration of that substrate to tremendous amounts to get to that maximal velocity. Now, if it took a lot of substrate to reach the maximal velocity, then it's going to take a lot of substrate to reach half of that maximal velocity. So your Km is going to be high. Now, if the affinity between your enzyme and your substrate is really high, that means your enzyme loves binding to the substrate. You just put a little bit into your reaction tube and that enzyme binds to it really rapidly. That means your enzyme reaches maximal velocity under low substrate concentrations because it's binding to it rapidly, and that results in a lower Km. So, the lower the Km, the higher the affinity between the enzyme and the substrate. Now, let's go back here. If we look at this plot, we could imagine doing this experiment, right? Maybe on our lysozyme. We'd put in different concentrations of cell wall substrate, our substrate, to give us the x-axis, and we would record the velocity of those reactions, and we could generate a curve like this. Now, it's difficult when you get a curve like this to figure out what Vmax is. This drew a line way up here. I don't know if that's where I would have drawn the line. Maybe I would have said this is Vmax. So why is it here instead of there? Or how do we pinpoint what Vmax is when we got a curve like this? And if we don't really know where Vmax is, then we can't know what half Vmax is. And if we don't know what half Vmax is, then we don't know what Km is. So it's important to move away from this curve to be able to calculate things like Vmax and Km exactly. And so what we're going to do is look at a Lineweaver-Burk plot. A Lineweaver-Burk plot takes our Michaelis-Menten expression, which is here, and it inverts it. And so instead of initial velocity, we're going to do 1 over initial velocity. Instead of substrate concentration as our x-axis, we're going to do 1 over substrate concentration. Okay. And we're going to arrange this equation into a line. So y is equal to mx plus b. That's our equation of the line. Y, instead of initial velocity, is 1 over initial velocity. The x, instead of being substrate concentration, is 1 over substrate concentration. And our slope is therefore Km over Vmax, and our y-intercept is 1 over Vmax. So we can take that same data that we had earlier and just plot it differently. Plot it with the inverse values, and we get this line. Now this line allows us to precisely calculate Vmax, because here the y-intercept is 1 over Vmax, and once we know Vmax, we can use the slope of this line to calculate Km exactly.